In this problem, we're looking at thin film interference effect. As liquid is poured onto a glass side, we see that the reflected light from a normally incident beam goes through one minimum and then another minimum, and we're asked to find the thickness of the liquid. Let's do a sketch of what's happening in this problem. I have a glass substrate, which is flat. I have a liquid, which is being poured on to some thickness d, and I have an incident ray from air. And what I'm asked to find is what the thickness of the liquid d is, which gives this particular signature, namely it's the second destructive minimum in the reflected light. Okay, so how are we going to set this up? Well, the phase difference due to the propagation through the liquid is equal to 2 times k times d. So this gives us the phase shift in radians. Now, in order to figure out whether or not we're looking at a maximum or a minimum, we need to consider the reflection from each interface and look for 180 degree phase shifts. At the top surface here, where we're going from air to the liquid, we're going from a lower index material to a higher index material. When that happens, we get a 180 degree phase shift. So it's going to be a 180 degree phase shift that just occurs from the reflection from the top part of the thin film. Well, let's look at the bottom. As the beam continues down, it reflects off the back face. But again, it's going from a lower index medium, 1.20, to a higher index medium, 1.50. So again, there's 180 degree phase shifts. So there's actually no net phase difference between the top surface reflection and the bottom surface reflection due simply to reflection. So now that we know that the phase difference due to the different path length, phi, is equal to 2kd, and we know that there's no phase difference between the two reflections, just from the nature of the reflections themselves, we can figure out where the second minimum is going to occur. In this problem, we're going to get a minimum whenever 2kd produces a 180 degree phase shift, or if we think in terms of radians, a multiple of pi phase shift. Not exactly a multiple of pi, sorry, but this relationship. Namely, when 2kd is equal to 2m plus 1 times pi, that is pi, or 3 pi, or 5 pi, or 7 pi, the reflected light from the top will be 180 degrees out of phase, or pi radians net out of phase, from the reflected light at the bottom. And we'll get destructive interference and a minimum in the reflection. Now we're told in the problem that we're actually looking for the second minimum. Well, the first minimum will occur at m equals 0, and then the liquid will get thicker and thicker, and eventually there'll be another minimum at m equals 1. Namely, in this problem, we're looking for the thickness where 2kd is equal to 3 pi, and that gives us the location of the second destructive interference point. Well, k is equal to 2 pi over lambda. Now, we have to be careful. We have to use the wavelength inside the medium. And so, if lambda naught is the vacuum wavelength, we have to multiply this times the index of refraction in order to get the shortened wavelength inside the medium. So now I can write down a complete expression that involves d, namely 2 pi over lambda naught times the index of refraction. That gives us a k in the material, times 2, we go down and back, times the separation d. It will be equal to 3 pi at this destructive point. Okay, so let's put in the numbers. It's 2 pi over 500 nanometers times 2 times the index, 1.20, times the separation d is equal to 3 pi. Well, we can rearrange these things and solve for d, which is pretty straightforward. We find that d is equal to 313 nanometers.